The 21st century has brought unprecedented technological advancement, but it has also brought an unprecedented energy challenge. Our current reliance on fossil fuels is unsustainable, both for the environment and for our energy security. Climate change is a very real threat, and we need to find new sources of clean energy to power our world. Traditional renewable energy sources such as solar and wind power are an important part of the solution, but they are not enough on their own. These sources are intermittent, meaning that they are not always available when we need them. We need a source of energy that is both clean and reliable. Quantum mechanics is a branch of physics that studies the behavior of matter and energy at the atomic and subatomic levels. It is a world where energy exists in discrete packets called quanta, and where particles like electrons can behave like waves. One of the most startling discoveries of quantum mechanics is that the vacuum of space is not empty at all. Instead, it is teeming with virtual particles that are constantly popping in and out of existence. These virtual particles, governed by Heisenberg's uncertainty principle, create fluctuations in the vacuum's energy, resulting in a background energy that permeates all of space. This background energy is what we call zero-point energy. For decades, the idea of harnessing this energy was relegated to the fringes of science. However, recent breakthroughs in our understanding of quantum mechanics and advancements in nanotechnology have brought us closer than ever to making ZPE a reality. We will explore the fundamental principles of ZPE, examining the quantum vacuum and the nature of these energy fluctuations. We will also delve into the technological advancements that are making ZPE extraction a tangible possibility. Our journey will take us through the step-by-step process of ZPE extraction, from stabilizing the quantum vacuum to converting this energy into a usable form. We will uncover the technological marvels that make this possible, such as quantum sensors, fractal energy collectors, and advanced quantum batteries. The implications of harnessing ZPE are far-reaching. Not only could it revolutionize the energy industry, providing a clean and limitless alternative to fossil fuels, but it could also pave the way for a new era of technological advancement. Imagine a world powered by quantum batteries where energy scarcity is a distant memory. This is the future that ZPE offers, and this video aims to be your guide to this exciting new frontier. In the world of classical physics, a vacuum is defined as a space entirely devoid of matter. Picture an airtight container from which all air and particles have been removed. In this classical vacuum, there is nothing, no activity, and therefore no energy. However, the quantum world, a realm governed by uncertainty and fluctuations, paints a drastically different picture. The quantum vacuum, unlike its classical counterpart, is far from empty. It is a dynamic and seething sea of energy, a realm where particles are constantly flickering in and out of existence. This phenomenon, arising from Heisenberg's uncertainty principle, dictates that we can never simultaneously know both the position and momentum of a particle with perfect accuracy. This inherent uncertainty leads to fluctuations in the vacuum, giving rise to virtual particle-antiparticle pairs, such as electrons and positrons, that emerge from nothingness for infinitesimal fractions of a second before annihilating each other. These fleeting particles, though not directly observable, leave their signature on the fabric of space-time. Their incessant creation and annihilation generate a background energy that permeates the entire universe. This fundamental energy, present even at absolute zero temperature, is what we call zero-point energy. The concept of zero-point energy has profound implications for our understanding of the universe and our potential to access a virtually limitless source of clean energy. The energy density of the quantum vacuum is staggering, estimated to be far greater than the energy density of any known conventional energy source. To put it into perspective, some physicists theorize that the zero-point energy contained within a single cubic centimeter of empty space could potentially boil all the oceans on Earth. While this is still a topic of debate and further research, it highlights the sheer magnitude of this untapped energy reservoir. The allure of zero-point energy lies not only in its vast abundance, but also in its inherent qualities. Unlike fossil fuels, which release harmful pollutants into the atmosphere, ZPE is a clean energy source, producing no greenhouse gases or toxic byproducts. Moreover, it is omnipresent, available anywhere in the universe, eliminating the geographical constraints associated with other renewable sources like solar or wind energy. If we could learn to effectively harness zero-point energy, we could usher in a new era of energy abundance and sustainability. Despite its immense potential, harnessing zero-point energy is a daunting task, fraught with complex scientific and technological challenges. The primary hurdle lies in finding a way to extract usable energy from these quantum fluctuations without violating fundamental laws of physics. Remember, these virtual particles exist in a state of delicate balance. Extracting energy from them requires careful manipulation of this balance without disrupting the very fabric of space-time. One promising avenue of research focuses on manipulating the Casimir effect, a phenomenon that demonstrates the existence of zero-point energy. The Casimir effect describes the attractive force between two uncharged, perfectly conducting plates placed in a vacuum. This force arises from the difference in the zero-point energy density inside and outside the plates, suggesting that manipulating the boundaries of the quantum vacuum could hold the key to extracting usable energy. However, practical applications of the Casimir effect for energy extraction are still in their infancy, requiring significant breakthroughs in material science and nanotechnology. The journey towards harnessing zero-point energy begins with a delicate and crucial step, preparing the quantum vacuum for energy extraction. In its natural state, the quantum vacuum is a chaotic sea of energy, with virtual particles popping in and out of existence in a random and unpredictable manner. This inherent randomness makes it difficult to extract usable energy directly. Imagine trying to fill a bucket from a raging ocean using a tiny cup. The chaotic motion of the waves makes it nearly impossible to collect a significant amount of water. Similarly, to harness ZPE, we need to find a way to calm the chaotic sea of the quantum vacuum. This is where the concept of coherence comes into play. In a coherent system, the individual components act in unison, creating a more ordered and predictable state. Think of a laser beam, where all the photons are oscillating in phase, creating a focused beam of light with immense energy density. Similarly, to extract usable energy from the quantum vacuum, we need to induce a state of coherence, aligning the quantum fluctuations and transforming the chaotic sea into a more organized and manageable energy source. Once a degree of coherence is established within the quantum vacuum, the next step involves the precise and controlled extraction of zero-point energy. This is where advanced technological components, specifically designed to interact with the quantum realm, come into play. One such component is the fractal energy collector, a nanoscale device engineered with intricate, self-repeating patterns that mimic the fractal geometry found throughout nature. These fractal patterns possess a unique ability to interact with a wide range of frequencies, allowing them to resonate with the quantum fluctuations of the vacuum. Think of a radio antenna tuned to a specific frequency. The antenna resonates with electromagnetic waves of that frequency, allowing it to receive radio signals. Similarly, fractal energy collectors act as antennas for zero-point energy, resonating with the quantum fluctuations and channeling the energy towards a conversion and storage system. The entire extraction process is carefully monitored using an array of quantum sensors, ultra-sensitive devices capable of detecting and measuring the subtlest changes in the quantum vacuum. These sensors provide real-time feedback, ensuring that the extraction process remains stable and preventing any disruptions to the delicate balance of the quantum realm. The energy extracted from the quantum vacuum exists in a raw form, unsuitable for directly powering our devices and technologies. This is where the crucial step of energy conversion takes place, transforming the raw quantum energy into a stable and usable form, typically electricity. This conversion process relies on the principles of superconductivity, a phenomenon where certain materials at extremely low temperatures exhibit zero electrical resistance. Superconducting materials play a critical role in ZPE conversion, allowing for the efficient flow of energy without any loss due to heat dissipation. Imagine a water wheel connected to a generator. The flowing water turns the wheel, which in turn powers the generator to produce electricity. Similarly, in a ZPE conversion system, the raw quantum energy is channeled through superconducting coils, inducing a flow of electrons and generating a usable electrical current. Maintaining stability throughout the entire extraction and conversion process is paramount. Any fluctuations or disruptions in the quantum vacuum could lead to a phenomenon known as decoherence, where the carefully established coherence collapses and the energy extraction process grinds to a halt. To prevent this, sophisticated feedback mechanisms and adaptive systems constantly monitor and adjust the extraction parameters, ensuring a continuous and stable flow of zero-point energy. After a predetermined cycle of energy extraction and conversion, the ZPE system undergoes a controlled reset process. This reset is crucial for maintaining the long-term stability and efficiency of the system. Think of it like allowing a farmer to let a field lie fallow after a harvest, allowing the land to replenish its nutrients and prepare for the next growing season. During the reset phase, the flow of energy from the quantum vacuum is temporarily halted, allowing the system to return to its baseline state. This involves recalibrating the quantum sensors, fine-tuning the fractal energy collectors, and ensuring the superconducting components are maintained at their optimal operating temperatures. Once the reset is complete, the ZPE extraction process can resume, drawing upon the virtually limitless energy of the quantum vacuum. This cyclical process of extraction, conversion, and reset ensures the continuous and sustainable operation of the ZPE system. The ability to repeatedly tap into the zero-point energy without depleting it or causing harmful environmental impacts is one of the most compelling aspects of this technology. It promises a future where energy scarcity becomes a relic of the past, replaced by a paradigm of energy abundance and sustainability. At the heart of any zero-point energy extraction system lies a technological marvel known as Zepihot, an acronym for Zero-Point Energy Harvesting and Optimization Technology. Zepihot is not a single device, but rather a sophisticated system of interconnected components, each playing a crucial role in taming the quantum vacuum and transforming its energy into a usable form. Think of Zepihot as the conductor of an orchestra, coordinating the actions of various instruments to create a harmonious symphony. In this case, the orchestra consists of advanced materials, nanoscale devices, and cutting-edge quantum technologies, all working in concert to extract, convert, and manage the flow of zero-point energy. One of the key components within Zepihot is the coherence engine, a device responsible for inducing a state of coherence within the quantum vacuum. This engine utilizes a combination of precisely tuned electromagnetic fields and specialized materials to align the quantum fluctuations, transforming the chaotic sea of virtual particles into a more ordered and predictable energy source. The coherence engine acts like a shepherd guiding a flock of sheep, gently nudging the quantum fluctuations into a more manageable state. This controlled coherence is essential for efficient energy extraction, allowing the system to draw upon the zero-point energy without disrupting the delicate balance of the quantum vacuum. Operating in the realm of the infinitesimally small zero-point energy extraction demands an equally exceptional level of precision and control. This is where quantum sensors, the eyes of the Zepihot system, come into play. These ultra-sensitive devices provide real-time monitoring of the quantum vacuum, ensuring the stability and efficiency of the entire extraction process. Imagine a tightrope walker traversing a high wire relying on a balance pole for stability. The slightest gust of wind could send the walker tumbling, but the pole provides feedback, allowing for adjustments to maintain balance. Similarly, quantum sensors provide constant feedback on the state of the quantum vacuum, allowing the Zepihot system to make real-time adjustments and maintain optimal energy extraction. These sensors are designed to detect the subtlest changes in the quantum vacuum, such as fluctuations in energy density or shifts in the coherent state. They act like highly sensitive microphones, picking up the faintest whispers of the quantum world and relaying this information back to the Zepihot control system. This constant stream of data allows the system to adapt to any changes in the quantum vacuum, ensuring a smooth and stable energy extraction process. The sensitivity and precision of these quantum sensors are crucial for preventing disruptions that could lead to decoherence, a collapse of the carefully established coherence that would halt the flow of zero-point energy. Harnessing the infinite potential of zero-point energy requires an equally revolutionary approach to energy storage. This is where quantum batteries, devices capable of storing and releasing energy at the quantum level, come into play. Unlike conventional batteries that rely on chemical reactions, quantum batteries exploit the principles of quantum mechanics to store energy in a more efficient and potentially limitless manner. Imagine a vast reservoir capable of holding an immense volume of water. This reservoir represents the potential of zero-point energy. Now, imagine a network of interconnected vessels, each capable of holding a specific amount of water and releasing it on demand. This network represents the concept of a quantum battery, where energy is stored in discrete quantum states and released with high efficiency. One promising approach to quantum battery design involves using superconducting materials to create quantum wells, energy states where electrons can exist at specific energy levels. By manipulating these energy levels, it is possible to store and release energy in a highly controlled manner. The development of efficient and scalable quantum batteries is crucial for realizing the full potential of zero-point energy. These batteries would not only provide a means of storing the vast amounts of energy extracted from the quantum vacuum, but could also lead to a new generation of energy storage devices with unprecedented capacity and efficiency. The successful harnessing of zero-point energy holds the potential to revolutionize the energy landscape as we know it, ushering in an era of clean, abundant, and universally accessible power. Imagine a world where energy scarcity is a distant memory, replaced by a paradigm of energy abundance, where homes, businesses, and entire cities are powered by the very fabric of space itself. The implications for various sectors of the global economy are profound. Take, for instance, the transportation industry, currently heavily reliant on fossil fuels. ZPE-powered vehicles, equipped with compact yet powerful quantum batteries, could travel vast distances without the need for refueling, significantly reducing carbon emissions and transforming the automotive landscape. The impact on urban infrastructure would be equally transformative. Cities could become self-sufficient energy hubs, their power grids fed by local ZPE extraction systems. This decentralized energy model would not only reduce reliance on centralized power plants, but also enhance grid resilience, making cities less vulnerable to blackouts and energy disruptions. Moreover, industries that require massive amounts of energy, such as manufacturing, mining, and data centers, could significantly reduce their environmental footprint by transitioning to ZPE power. This shift towards a clean and sustainable energy source would have a ripple effect throughout the global economy, creating new industries, jobs, and economic opportunities. Beyond its transformative impact on the energy sector, zero-point energy has the potential to unlock a new era of technological advancement, particularly in the realm of quantum technologies. Quantum computing, a revolutionary paradigm that harnesses the principles of quantum mechanics to perform complex calculations, stands to benefit immensely from the availability of ZPE. Quantum computers are notoriously energy-intensive, requiring extremely low temperatures and precise control mechanisms to maintain the delicate quantum states of their qubits, the building blocks of quantum information. ZPE, with its potential for near-perfect energy efficiency and miniaturization, could provide the ideal power source for these next-generation computers. Imagine a world where ZPE-powered quantum computers accelerate drug discovery, optimize complex logistics networks, revolutionize materials science, and unlock new frontiers in artificial intelligence. This fusion of ZPE and quantum computing could lead to breakthroughs in medicine, materials science, artificial intelligence, and countless other fields, pushing the boundaries of human knowledge and innovation. Furthermore, ZPE could revolutionize communication technologies, enabling the development of ultra-fast and secure quantum communication networks. These networks, impervious to hacking and eavesdropping, would rely on the principles of quantum entanglement to transmit information, ushering in a new era of secure and reliable global communication. The long-term sustainability of our planet hinges on our ability to transition from fossil fuels to clean and renewable energy sources. Zero-point energy, with its virtually limitless and environmentally benign nature, presents a compelling solution to this global challenge. By tapping into the fabric of space-time itself, we can potentially power our civilization without depleting natural resources or polluting the environment. Imagine a future where the reliance on fossil fuels is a relic of the past, replaced by a global energy infrastructure powered by ZPE. Smog-choked cities could breathe freely again, greenhouse gas emissions would plummet, and the threat of climate change could be effectively addressed. The global impact of ZPE technology extends far beyond environmental sustainability. Access to abundant and affordable energy has the potential to uplift communities, alleviate poverty, and foster economic development worldwide. Imagine remote villages powered by off-grid ZPE systems, no longer tethered to the limitations of traditional power grids. The widespread adoption of ZPE technology could foster greater global cooperation as nations transition from competition over scarce resources to collaboration in harnessing this universally available energy source. In a world powered by ZPE, the pursuit of a sustainable and equitable future for all becomes a tangible possibility. Navigating the quantum frontier, technical and theoretical roadblocks. While the promise of zero-point energy is tantalizing, transforming this theoretical concept into a practical reality requires overcoming formidable technical and theoretical challenges. The quantum realm, with its inherent uncertainty and counterintuitive laws, presents a unique set of obstacles that must be meticulously addressed. One of the most significant hurdles lies in maintaining the delicate state of coherence within the quantum vacuum. As explained earlier, coherence is crucial for efficient energy extraction, but it is easily disrupted by external factors, leading to decoherence, a collapse of the ordered state, and a halt in the energy flow. Maintaining this delicate balance within a system as sensitive as the quantum vacuum is akin to trying to build a house of cards in the middle of a hurricane. Another challenge lies in developing materials capable of withstanding the extreme conditions required for zero-point energy extraction and conversion. Superconducting materials essential for efficient energy flow typically operate at extremely low temperatures, close to absolute zero. Maintaining these cryogenic temperatures on a large scale presents a significant engineering challenge and adds complexity to the design and implementation of zero-point energy systems. On the theoretical front, our understanding of the quantum vacuum and its interaction with matter is still evolving. While quantum mechanics provides a framework for understanding zero-point energy, many questions remain unanswered. Further theoretical breakthroughs are needed to refine our understanding of how to effectively and safely extract energy from the quantum vacuum without violating fundamental physical laws. From laboratory to life, scaling up zero-point energy for global implementation. Assuming we overcome the technical and theoretical hurdles associated with zero-point energy, the next grand challenge lies in scaling up this technology from laboratory experiments to a level capable of powering our world. This transition from laboratory curiosity to global energy solution requires a multi-pronged approach, addressing issues of scalability, cost, infrastructure, and public acceptance. One of the primary concerns is the scalability of zero-point energy technology. While we may achieve promising results in controlled laboratory settings, replicating these results on a scale large enough to meet global energy demands is a significant leap. Imagine trying to scale up a delicate laboratory experiment designed for a few milliliters of fluid to handle the volume of an entire ocean. Cost is another crucial factor. Developing and deploying any new energy technology requires significant financial investment, and zero-point energy is no exception. Initial production costs are likely to be high, potentially hindering widespread adoption. particularly in developing nations. Overcoming this cost barrier requires innovative engineering solutions, economies of scale, and potentially government subsidies or incentives to encourage investment and accelerate deployment. Integrating zero-point energy technology into our existing energy infrastructure presents another set of challenges. Our current power grids, designed for centralized power generation and distribution, may not be compatible with the decentralized nature of zero-point energy, which could be harnessed locally. This transition might require a fundamental redesign of our energy infrastructure, a costly and complex undertaking. The ethical dimensions of unlimited power, navigating societal impact. The prospect of harnessing a near-limitless energy source like zero-point energy raises profound ethical and societal questions that demand careful consideration. Just as the discovery of nuclear fission brought about both immense promise and unprecedented peril, the ability to tap into the very fabric of space-time comes with its own set of potential benefits and risks. One of the most pressing concerns is the potential for misuse of this technology. Access to unlimited energy could be a double-edged sword, potentially falling into the wrong hands and used for destructive purposes, just as nuclear technology can be used for both energy generation and weapons development. The potential for weaponizing zero-point energy cannot be ignored. Furthermore, the widespread adoption of zero-point energy could have unintended consequences for the global economy and geopolitical landscape. Nations currently reliant on fossil fuel exports could face economic upheaval, potentially leading to instability and conflict. The transition to a zero-point energy-powered world requires careful planning, international cooperation, and equitable distribution of benefits to avoid exacerbating existing inequalities. Another ethical consideration is the potential impact on human behavior and values. The abundance of energy provided by zero-point energy could lead to complacency, potentially hindering innovation and our drive for efficiency. Moreover, the control and distribution of this technology raise questions of access, ownership, and the potential for monopolies to emerge, controlling this vital resource. At the cusp of a new energy era, as we stand on the precipice of a new technological age, the pursuit of zero-point energy embodies humanity's relentless quest for knowledge and its unwavering commitment to securing a sustainable future. The journey through the intricacies of the quantum vacuum, the exploration of its boundless energy potential, and the ingenious technological advancements aimed at harnessing this power have illuminated a path towards a future where energy scarcity becomes a distant memory. The challenges that lie ahead, though formidable, are not insurmountable. Just as the pioneers of flight dared to defy gravity, driven by an unyielding belief in the impossible, we too must embrace the audacity of imagination and the power of human ingenuity to overcome the technical and theoretical roadblocks that stand between us and the realization of zero-point energy's full potential. The successful harnessing of zero-point energy holds the power to reshape our world in profound ways, extending far beyond the simple provision of clean and abundant energy. It has the potential to reshape global power dynamics, revolutionize industries, and propel us into a new era of technological advancement, driven by the limitless possibilities of the quantum realm. Imagine a world where energy poverty becomes a relic of the past, where developing nations are empowered with the same access to clean and affordable energy as their developed counterparts. Imagine cities free from the suffocating grip of smog, powered by the very fabric of space itself, their inhabitants enjoying a quality of life previously unimaginable. The road ahead, a collaborative endeavor. The realization of this transformative vision, however, requires more than just scientific breakthroughs and technological marvels. It demands a global collaborative effort, transcending national borders and political ideologies, uniting humanity under a common goal, securing a sustainable future for generations to come. Scientists, engineers, policymakers, and industry leaders must work together, sharing knowledge, resources, and expertise to overcome the remaining technical hurdles and facilitate the smooth transition to a zero-point energy-powered world. Open collaboration and the free exchange of ideas will be paramount in accelerating the development and deployment of this game-changing technology. The ethical considerations surrounding zero-point energy, particularly the potential for misuse and the need for equitable distribution of benefits, must be addressed proactively and transparently. International agreements and regulatory frameworks are needed to ensure responsible development, prevent weaponization, and guarantee that the benefits of this transformative technology reach all corners of the globe. The journey towards harnessing zero-point energy is not just a scientific endeavor, it is a testament to the indomitable human spirit, our unwavering belief in our ability to overcome seemingly insurmountable challenges and shape a brighter future for all. It is a journey that demands courage, collaboration, and an unwavering commitment to the well-being of our planet and all its inhabitants. A sustainable future, powered by the quantum vacuum. As we venture further into the 21st century, the pursuit of zero-point energy stands as a beacon of hope, a testament to our potential to transcend limitations and create a future where energy abundance and environmental sustainability go hand in hand. The journey ahead will undoubtedly be challenging, demanding both scientific rigor and ethical responsibility, but the potential rewards are immeasurable. Imagine a world where children, no matter where they are born, have access to clean and reliable energy to power their homes, schools, and dreams. Imagine a world where the air is clean, the climate stable, and the natural world thrives in harmony with human progress. This is the promise of zero-point energy, a promise rooted in the fundamental laws of the universe, a promise that, with unwavering dedication and collaborative spirit, we can and will fulfill. The journey has just begun, and the destination, though still on the horizon, shines brightly, beckoning us towards a future powered by the very essence of the cosmos. This future, a future where humanity coexists sustainably with its environment, powered by the boundless energy of the quantum vacuum, is a future worth striving for, a future that, together, we can create.